Okay,
So,
I think we're good.
okay, so today we're gonna talk about connections on fiber bundles and parallel transportation. Okay, so we're gonna do the exact opposite of the title. We're gonna first talk about parallel transportation. So let's do that. So the roadmap is we're gonna talk about some questions and the need for parallel, sorry, transportation. Then we're gonna try to find what are the conditions to have a good, well-defined parallel transportation. Conditions to have nice parallel transportation. And then we're gonna talk about some definitions that are called the vertical and horizontal fibers, spaces, whatever. And then lastly, we're gonna define what connection is on the fiber bundle. In two ways, because why not? In two ways. It's buy one, get one free. Okay, so very briefly speaking, so let's give the motivation for listening to this talk. Um, First of all, we wanna answer this question. So let me write this. So we have a question. Question is, if you have a vector bundle this, and the section this, and the vector x in the tangent space of a point x and m, what is meant by the directional derivative dsx x? Okay, so this is the first question that we're gonna ask. So everybody here knows what a directional derivative is because we all took 257. Um, and the question is, you can define the directional derivative on the manifold, and that makes sense, but then you ask to define it on the tangent space. And then it's a little bit confusing because um the you're working on a vector bundle, and it might not be the trivial bundle in the first place. So how do we find this? Like directional relative to what? Like, what's going on? So let's split this into parts. So let's draw this. Um, so this is our space M, and then we have this total space E. We have this little x here, and this is maybe tangent to it like this. So this is the big X. Now, okay, before we draw further, let's write what this guy actually does. So this is a linear map. This is linear, and it's from the tangent space of X to the tangent space of the section, where X sits in the section in E. So we have a section. So for example, if this is the section, this is S, and then X is sitting here, right? Because this is the thing that the section crosses in E. So we were looking at so we want to take this big X that's tangent to X in M, and then we wanna send it something tangent to this point here. So this is S of X. So this means that we're taking tangent vectors to n to tangent vectors to e. So we're looking for something like this. Now, we want to define it in a way that we usually define derivatives. So we can try to write this. So we can say, okay, let's take this guy and say this derivative at x is, sorry, but this is at t equals 0 because we want to know it at x. And then we can write this as comma 0 divided by t. Right, so this is just the old derivative definition we know, where the path at 0 is big X. So what does this mean? So this means that we have, so assume that these are like looped together, so like these are glued. Let me do it like, let me make it seem like that. Okay, so this is the space and that's E. So what we do is we make a path, and path is like this, right? I'm gonna change the big X. At X, it's the tangent to it is big X, we know, right? So writing this basically means that we want to take this big X and actually make it travel along the path and somehow sit here. Somehow. Now the problem here is, um, one second, I deleted way too many things. The problem here is this is not very well defined because the path is not going to stay on one fiber. It might not stay on the same fiber all the time. It might go between the fibers. So you cannot just write this. Oops. Sorry. So this, we can't just write this.
So this is a good place to stop and ask the audience a question. So why is it that if I go to a different fiber, I cannot write down an expression like this? So question for the audience. What's wrong with this expression if um, I move from one fiber to another of my vector bundle? Even if you don't know, just unmute and start saying stuff. And we'll correct you or give you hints. You know, what are we doing in this expression? I'm taking S of gamma of t and doing what? Trevor or Murin? I'm doing taking S of gamma of t and doing what to it? Just look at the expression. You're muted if you're not saying it. Okay, sure. Murin, go. You can just say, go for it if you know the answer. Because I don't know, maybe he's just not here right now.
Aren't you just like taking a derivative of your like your past and then you might move in like the wrong direction?
That's not quite right. That's not quite the question that's being asked. The question is, suppose I just wanted to write down this expression, right? This
Yes.
expression that's circled in red. Here I have S of gamma of t, and then what do I do to it?
Oh, you're
Yes.
uh
I subtract what?
yeah, you subtract like the M point to the first point or
Yeah, so I
whatever.
subtract S of gamma of t from S of gamma of 0. But does
Yeah.
this statement make sense always? Does the statement make sense?
Yes. Like the subtraction makes sense.
Why does so suppose gamma of t and gamma of 0 are different points, right?
Yeah.
This means that S of gamma of t is a vector in the fiber above gamma of 0, and
Yeah.
S of gamma of t is a vector in the fiber above gamma of t. What does it mean to
Yes.
subtract those two things?
You're taking okay. So it's like between like it's a segment between those two vectors. You're
Well,
connecting them,
the
and
point
like
is it's
the
unclear
part in the
what this
middle isn't
means.
necessarily in the manifold.
So, like the point is exactly that if I have two vectors in different fibers, right, then I have no sense with which to subtract them or add them. So
Okay.
because I just don't have an addition operation defined on it. I only have an addition operation defined on vectors in the same fiber. So if I want
Yes.
to take a derivative in my vector bundle, I need to find a way to compare vectors in different fibers.
Okay.
So I need some additional information um, to be able to do this. And so now I guess we'll find out about what this additional information should be, how it should look like, and so on and so forth.
Yes.
Okay.
Okay. So yeah, as Ivan explained, this is not so well defined. So we don't know how to do this. It doesn't even make sense. So we're gonna try to find a solution to this. Now, what do we need? So first of all, sorry, I'm thinking I'm skipping something here. Okay, maybe not. So what we can see ds, let me go back to black. You can see this dx as a map from this to this. This is right. Yes. So now the problem, like we said, is that these guys are on different fibers. But they're close, right? But they're quite close. But they are close. So because these fibers are really close, and this is a nice bundle that we can work with, so it's not just random products that's unconnected, that the fibers go unconnected. So since this is a fiber bundle, and these guys are actually close, um, we can we can somehow find a connection between them. So connection name first appears here. So there is a connection between them. You just need to define this connection mathematically nice. So okay, so this was the first question that we're gonna consider. And a little quote from Monastrinsky is that okay, so he says that connections are actually introduced to define parallel transportation. And by parallel transportation, we mean exactly taking one thing and carrying it along a curve where how we carry the carried guy is just parallel to the first guy. Connections are introduced to define Parallel transportation. Okay, since it's already been 15 minutes, I'm gonna skip some parts here, which was basically just another point of view. Maybe we'll come back to it later. Okay, so oh, let's look at some examples. So what do we want for the parallel transportations? Let's assume that M is a two-dimensional manifold. Then for any X like this and a path gamma that's completely on M, such that it starts at X, we are gonna carry X along gamma. And these will be the smooth family tangent vectors. Okay, I will write one more thing and then I will start drawing. In fact, this gives a smooth family of isomorphisms. This is little x, sorry. You should always ask me if you're not sure about if something is big X or little x, because it really matters. With at zero, this family should equal just identity. Okay, so now let's understand what we mean. So we have this M. Okay, we said two-dimensional, so let's draw a sphere. This is M, and let's have a path. Let's draw it like this. Now let's say this is X, and we have a path like this. And we have this X like this. What we do is we just carry it. Literally carry it. But we want all of them to be parallel to each other. So we're calling these guys XT. So these are the smooth family of tangent vectors. And since their starting point change, these are elements of whatever gamma t is at that point. So since we can do this for any vector that we choose, any big X that we choose, right? So there's no constraint on that. We can just and these are vector spaces. Let me write it like this. Are vector spaces. And we can do this for every X in them. So what we say is, okay, instead of writing for one singular vector that we chose, let's write the general isomorphism between these vector spaces, and we call them P gamma T's. Now, there are some problems here because at this point, these are depending on gammas. Dependent on gamma, not just starting and ending points. So to convince you on this, first I was not convinced. Maybe this is not the best drawing. This is not the best. growing. At first, I read this, I was like, nonsense. So this, because we're carrying it, so it's parallel all the time, right? So that wouldn't make sense if these are actually dependent on gamma and so on. But let me convince you to this. So convincing. So let's assume we have the sphere M, like before. And our path will be this. So we start on the equator, we go for a while, and then we go straight up north, and then we go down. So the start and ending points are the same. So it shouldn't vary, right? And then we chose our x to be here, and then our big X will be this. Now, as we carry this guy, so now these are all parallel, right? At this point, it's all parallel. Now, we have to continue this way. So these are parallel. That makes sense to you because this is a sphere. You have to go this way. Now, when we come here, again, we want to be parallel to this guy. So we go down. Tada, it's completely something different. So with what we have in mind of a parallel translation, it doesn't really work. It really depends on the path. You don't obtain the same thing on closed paths. You could have gone a totally different path and it will have been the same thing, or something different from these two guys too. And these are not the same. So this doesn't really work. So what we want to do is we want to solve this problem. We want to define a parallel transportation somehow and make it independent of the path. So that will be our first condition. We'll write them nicer in a second. But before that, let's talk about them a little more. So we talked about this for the
Well,
two-dimensional
sorry.
manifold.
So
Yeah,
small correction. We want it to be not completely independent of the path, but
that's
independent
true.
of equivalent paths under
Yes,
homotopy.
homotopy.
Yeah.
So what we want to do is, yes, that's true. So we want them to only depend on the starting and ending points. So that will be the true reason. Well, let's say that we want p gamma t's to be.
I mean, well, once again, it's not just start and ending points because I could have two
If you
paths
have
with
holes,
yes,
yes,
exactly.
that you're right again.
So
Okay, yeah. So let me spell dependent on
to
paths
to
up to
depend
homotopy.
yes up to continuous deformation. Let's or something like this, which is
Okay,
homotopy, but people might not know the term. So
I think everybody here has taken 3 to
I mean,
7, but anyway, yeah,
let's not assume.
yeah. Okay, so up to continuous deformations for one set of homotopy, which means that if you have two paths, something like this, and there are no holes in between, you can basically take this and push it, right? So consider this like a rope with two endpoints fixed, and you can just push it. And by pushing it, you can obtain this guy from the first one. But if there was a hole, then you couldn't do that, right? So if there was a hole like this here, and whatever you do, you push, you try to maybe take it out and get away, but there's a hole, so you cannot make it cross the hole. So these are not homotopic. These are homotopic. So we want to make our parallel transportations independent of the paths that can be pushed from one to each to the other. Okay, so now we talked about this for the two-dimensional case. Let's actually write it for the more general case. So for a general vector bundle, E to M, you want to associate with any path. It's smooth family of parallel transportation isomorphisms with at 0 we want it to be the identity. So okay, so you can ask me, what's the difference? You just wrote this above. No, I wrote this for M. So we were staying on M. We were staying on our base manifold all the time. Now we're asking, what if we have a bundle and we want to do this parallel transportation? And we want to do the parallel transportation on the bundle, on the on the universal space. So that's even more complicated. And we know that these are not unique. But we also know that these are not arbitrary too, but not random, but not random too. So let's try to understand what are their types. So what can they be? So we know that they depend on the path up to homotopy. So there might be two paths that are not homotopic to each other, that you cannot push one to each the other. And then you will have two different kinds of parallel transportations. But at the end of the day, they have to be related somehow too, because they're not gonna be just you can't just write anything to be a parallel transportation. That wouldn't make sense. Okay. So let's take gamma t in M to be a smooth path. And at 0, it's little x. And we are given a smooth section along gamma, which means that we're looking for a section in this. Oh, sorry, I started to write Turkish, sorry. Um, section in this. So if this is confusing, it shouldn't be. This just means that we have this base space M, and then we have this gamma. This is gamma, and then we have this total space. And then we just look at the total space where gamma can come from, how to lift it up. And then we take its section on this area. This is this, and then that will be the section. So a section will just be a section as usual.
Yes. So the idea is I have my base space. I know how to move around in my base space. The idea is to define, if I was to start in the bundle at some point and follow the path on the base space of gamma, to know that if I knew a starting point of where I start at with in the fiber bundle, then there was some sense in which I could follow the path gamma on the base space, but somehow in the fiber bundle. I don't
Yeah.
know if that makes sense. Yeah.
Okay. Is there questions or someone told or not? I don't see everyone, so. Okay. Sorry, maybe I heard. So then what we do is we define something called the covariant derivative of S along gamma to be this. So now this is a new word that we just learned, and I'm gonna talk about this very briefly, but for now let's write the mathematical thing. So we define this to be so we write it like this. and evaluated at t equals 0. Okay, now what's the difference here? So now above we had these guys that lived on different fibers, whereas here what we do by writing this is we make them live on the same fiber. So these are living on the same fiber, and I'm gonna draw that in a second. Let's write that. Oops. These live together, same fiber. Indeed, I don't even have to say this because this is a single thing. So you have to realize that this is actually not some or different of something. So these are just actually, this is a single thing. So it lives on a fiber. So we're good. Okay, so a little bit on covariant derivatives. So the catch is these guys have been introduced in late in 20th century 20th century by Ricky Barbastro and Levi Givita. I always thought Levi Givita was two people. Apparently it's one. It's not two people. But that's one guy. One guy. As a generalization of the directional derivative. So this was introduced as generalization of directional derivative. And they needed this because, so their initial idea was to do this. So if we have, so they wanted to define this, where this is a vector starting at P, and this is a vector field around P, or around the neighborhood of P, will have been a better way to say this, though. And they wanted to define this. So how to do this and how to make it independent of the coordinates they use. So that's how they came up with it, and it has something to do with Christoffel symbols and other areas of physics that I'm not going to talk about. But if you're interested, Monastrinsky has said nice stuff on them, but I'm not going to discuss them because I won't have time. Okay, now back to the work. So what does this mean? So we have this section. So S of t is just, so on the gamma there are t's, right? So it's parameterized, and we took a section of the preimage of this gamma row. So you can say that, okay, so at t, this is here, and maybe it'll be here on the section. So this point is S of t. So that's what's meant with that. And this parallel transportation, what it does is, so normally, let's see where it comes from. So it comes from this. So it comes from where gamma starts, which is here, and it pretty much of where gamma starts, which is here, and it goes to here, right? So if S of t is here, and we look at the preimage of the parallel transportation, this means that whatever vector we have here, we carry it back to here. the starting point, which is why it's evaluated at t equals 0. Now, the good part of this definition is you can actually generalize this. You don't have to evaluate it at t equals 0. You can evaluate it at any point at t equals. What you have to know is only this. As long as you know this guy, you can just carry it along the section with some parallel transportation that which we're going to define nicely, and then you'll be happy, and then you will have this guy that we actually want to define in the beginning here. So instead of writing this, we now have a solution to how to do it by just taking stuff and carrying them parallel. Okay.
Yes. So roughly, the problem we had before was that we had vectors in different fibers. If you had a way to transport the kind of vector at a later time back to the initial fiber and then compare them, then you're good. That's it.
Yes. So now let's write this even in a more general sense. So what our problem was that we couldn't define directional derivatives on these bundles. So, okay, I have to go back to black. So in the most, well, okay. So defining the covariant derivative. What do we know? We are given these data. And this, but this is actually at 0. Which isn't, so we know these. And then the derivative itself is defined as so Smx evaluated at big X is just this guy, which is now this is an element of Ex. So this, it's all well defined. So we're happy, we're good. So now we should ask, okay, we now have the motivation for defining the parallel transportation families, which are these. Now the question that we have is how to define these, because we know that they're not unique and they must have some conditions on them. So let's try to understand what conditions they need on them, what conditions we need on them. Conditions we need on guys. So, okay, time to change the paper. We need the definition of to be independent of gamma except for the tangent vector. Now we get to choose this. We have to choose this. This needs to be chosen. When I say independent of gamma, I always mean independent of gamma up to homotopy. This needs to be chosen. And the second condition we need is now see. Okay, let me write it and then let me explain it. Let me convince you, please. The map to sorry, my mother is calling. Just 1 second. Sorry. I have to text her, so we're gonna have a 2-minute break.
Yeah, that's okay. Let me see if I can zoom. Go ahead.
Okay. Okay, so it's resumed now, right? Okay, because I don't see. So I haven't told you what this is yet, but the need for this condition is coming from this. So we will understand this in a second. But the thing is, um, so assume that for any vector field, let me do this. For any vector field xm, the covariant derivative defines another section. Now, any sensible definition of derivative requires us to have this, right? And this to be linear for all x. Because we're working with vectors that are coming from the tangent spaces. So if we actually add them up in the tangent space first, that will give us another vector. And then what we're doing is we're just transporting some stuff and we're just placing them somewhere else nicely. So if we added two things in the first place and then said, okay, how does this go? How does this get carried to the other place? That has to be linear too. So this actually is very physical, and I think it makes lots of sense. Okay. Um, Now, to be able to define parallel transformations explicitly, to be able to define parallel transportations, we need another tool. We need a tool, which are the connections. Okay. So now this is the first half of the talk. And then we have the second half. The question I'm gonna ask is if people wanna give a break, we can give a break. Because I usually get bored after 50 minutes or so. Do people want a break? Everyone's happy? Everybody's going good for going for 1.5 hours?
Well, I guess, Trevor, is that a thumbs up for a break or for no break?
No, I can keep going.
Okay, keep going.
Okay,
Good.
amazing. I will have get bored in my own my own lecture, but okay. Um, so now the second half, connections on the fiber bundles. Definition. And now we're gonna define the vertical bundle. Let P from E to M be a fiber bundle. The vertical bundle is the sum bundle of tangent space of E to E defined by so this is the parentheses and the second one is C, even though they look the same, such that this is 0. Um, and then I'm gonna write one more sentence and then we're gonna start drawing. 0. Oops. Its fibers they're also denoted like CPE are called vertical subspaces.
Please draw a picture.
I will now. In a second, I will just gonna highlight these vertical bundle, and then now I'm gonna draw. So, what did we have? We have M. We have the total space. The map pi star is a map from this to this. Nothing else. Not very fancy. So what do we mean by saying that we're looking at elements such that under this pi star, their image is 0. So this means that if we project Kisi with pi star, then they don't have a image on M. So okay, so now let's consider the. Okay, let me draw it a little bit nicer. I will draw it a little bit bigger. So this is M. And this is E. So suppose we have this is X, and then this is the fiber standing over X. Now suppose we have a vector like this. This is tangent to this point. This guy is Xi. So Xi is an element of
Wait,
this.
sorry.
Yes.
Slight request. Could you be a little bit more pronounced with the curves in the C? I thought it was an open bracket for like a solid minute.
Yeah, I know. I know. That's what I tried to set here. So this is okay.
Thank
That's
you.
the best essay I've drawn in my life. Okay, yeah, that's good enough. So what we're asking for is this is so C is tangent to E, right? So this is still tangent. You have a cylinder and then you just put something on the cylinder that's still tangent then. Now if you make this project on M, that's going to be 0. Because well, if you make it project on tangent space of M, that's what we have to project on because it's a tangent vector. If you project it like that's not well defined. But if it's a tangent, but if you project it to tangent space over M, then we know how to project that, right? So now assume that it's actual difference. So it's actually pointing outward. So assume it's coming out of the page to you, and let's call this I don't know this. Call this eta. If you project this will come to something like this. So maybe I didn't draw it as nice, but what I wanted to draw was this. It's coming a little bit out of the page and to the side. If you project it, it will be this vector. Now this is also tangent to x, right? So this is p star eta, and this is an element in let's call this point. I don't know what let's call this point P. Maybe P is not a good name. Give me a letter. Let's call this A. And x is pi of A. Pi of A is x. Right? So this is true. Now, what we want in the vertical bundle is the guys who don't have an image if you project it to M. So this means that if you have something that's tangent to the point here at A, sorry. So if you have something tangent to here, we want to look at the subspace that is completely living on the fiber. What does it mean to completely live on fibers? It means that when you project it, it disappears because everything in the fiber gets projected to X. So if you have a tangent vector at A that lives on the fiber, so let's write this. So any tangent vector to A that lives completely on the fiber is projected down to 0. Because it's not a vector, it just gets projected to X. You don't have the vector anymore. Okay. So and looking at so this is the general thing. The general thing is called the vertical bundle. And if you look it above every point, you will have the vertical subspaces, which makes sense. Do I have anything else to say on this?
Yes, so I'll add a few comments. Is that so? The
Okay.
important thing is the vertical bundle. This is a sub-bundle of the tangent bundle of E. So you look at E and you look at kind of all the tangent vectors to it, and then you only look at the ones that are tangent along the fiber. Okay. And the point is that this is completely uniquely determined, right? If you know your fiber bundle and you know how the fibers go, then you can always look at all the vectors that kind of point in the direction along the fiber, and so that's completely uniquely defined, right? But then so I guess you'll say this in a second. But then yeah, I'll just stop here. That the vertical bundle is uniquely defined. But then the next
Yes.
thing we're going to look at is not going to be uniquely defined, and that's where we need to make a choice. Okay, go ahead.
Yes. Okay. So I have one more sentence here. Let me think to if I should write it or not. Yeah, okay. Just to write this in mathematics words, this means that this is actually this. So tangent to P and everything. Okay. On this one. So this is the fiber. So this means that we're looking at the tangent space of the fiber at that point. So it makes sense perfectly. And as Iman said, this is uniquely determined because if you know your fibers, then there's only one way to have your vertical bundle. So it makes sense. Okay. So now we're down 3 papers and then we have 1.5 to go. So what we're gonna do now is, okay, I'm gonna do a little bit tricky here. I'm gonna write a proposition. I'm not gonna prove it. The reason I'm writing this proposition is to give a relation on parallel transportation that gives motivation to define something called the horizontal bundle, horizontal spaces. Again, I'm not gonna write the proof. Am I allowed to do that, Iman?
Sorry.
Am I allowed to give the proposition but not write the proof?
Yeah, that's fine. That's fine.
Okay.
As long as you draw a picture that makes it completely obvious, then I'm convinced.
Okay. I'm not gonna draw a picture for this one, but I will explain it first. Okay, so assume the fiber bundle. Maybe I should have said that this is a fiber bundle from the start and not write it 100 times. But anyway. Now for all gamma t in M, and there is a smooth family of diffeomorphisms satisfying the usual thing that we wanted to be identity at 0 and 1 and 2. So 1 and 2 were here. Where are they? I lost them. Here. So these are 1 and 2. So we want them to be independent of gamma at the homotopy, and this guy to be linear. Then, so this is the assumption. Assume. Then, for each x in M and P in fiber of x over x, there uniquely exists a linear injection horde P, where horde is the horde of horizontal, but we don't know that yet. That's just a coincidence, and we use the same name. Such that horizontal P over this, which is horde P of big X, equals this. For all paths with starting point, so that's gamma of P. Moreover, the image of 4P is complementary to this vertical subspace in the tangent subspace, in the tangent space of P and E. Okay, so we know the assumptions. The assumptions were just what we were wanting to prove. So there's nothing to talk on them. But just what we say is if we have something like this, then there okay, so what does this mean? Let's talk about that. So let's draw this. This is M. This is E. We have this X, and then we have this fiber over X, so this is EX. And we choose a point here on this EX. This is P. Now what you're saying is if you have any vector that's tangent to X here, then there is the whole piece. Take this guy, make it go to something to tangent at P here. Now here comes a such that so this is X, so let's okay, let me write the name. So this is X, and this is what X is taking to with hor P. This is equal to this. Derivative of the parallel transportation.
Yes. So the idea is to kind of say that, okay, how does a direction on the base space, like what directions does that correspond to on E? What does that, what direction does that correspond to at a point P on E? And remember, this corresponds to choosing some kind of subspace at point P, which if you take this subspace and take the vertical subspace, then you get the whole kind of tangent space, right? But the point is that if the choice of the vertical space is unique, right? I know exactly how to go along the fiber. The choice of a complementary space is not unique. Why? Because I can choose a subspace like this, and that's going to give me the whole tangent space. Or I can choose a subspace like this. This is a different subspace, but it still gives me the same like total space. So that's why kind of the idea here is that the choice of parallel transport is equivalent to giving you the choice of kind of this horizontal subspace, which tells
Yes.
you like, where do I go on M? How does that correspond to where I go on the tangent bundle? And this choice defines some horizontal subspace.
Yes.
But the
So
important point is that it's a choice.
yeah. So the catch here is horizontal of P depends on the parallel transportation that we assumed in the first place. So we assume that we know how the parallel transport stuff. And then we said, okay, then the whole PX is going to be defined depending on how we parallel transport, like Ivan said. So this this makes so much sense to me. Maybe because I got used to it, but if it doesn't, I can try to explain it more. But that's the whole point. So we're just translating it through some gamma, and at the starting point of gamma, it's the tangent to the starting point is the big X, and we're transporting big X. That's why we're evaluating this derivative at t equals 0, so that what actually gets transported is the big X that we want to get transported. And we look at it at the point P, and the path was gamma, so this all makes sense. That's what we have been trying to write from the first place. Okay. So let's note this, the catch. So let's do this and say the catch P depends on the choice of S. Let me put an exclamation mark. Okay. So now we know that we have this structure, which we haven't defined yet, but we will soon, that is depending on the parallel transportation. So they're somewhat related, right? So now let's go ahead and define this. But so from the source I read, which is a source I quite like, I look at multiple ones, this was the best one I liked. It gives this proposition and then proves this proposition, which is just writing the intermediate steps of calculations. It's quite intuitive. And then it says, okay, because this is a true fact, then we should be able to define something called the horizontal subspace. Now let's do that. So they first point out this fact. Definition. Okay, actually, I'm gonna define the connection. Now we're defining a connection. A connection on the fiber bundle is a smooth distribution. I will say what this is in a second. Distribution. Yes, I will say what this is. HE on the total space such that so this is the vertical bundle we just defined. This is the tangent bundle, we know who is. And this is the new guide, the new smooth distribution that we just had the intuition to define from this proposition. And we say for any P in E, the fiber HPE in TPE is called the horizontal subspace at P. Okay, so what did we define? We defined the connection and we defined the horizontal subspace. Now let's say what smooth distribution is. A distribution is basically just a pointwise assignment of subspaces of the tangent spaces so it's just a fancy word for this. So just for every point you stick a subspace, well not stick, but you say this is the subspace I'm assigning, and you do it. So that's the whole thing. That's the whole point of distribution. And smooth comes from well, if the subspace is very smoothly from point to point, then it's called smooth. And let me note that too. If the subspace is smoothly from point to point, it is called smooth. That's the whole deal. So now let's read the definition again and see what it means. So we call a connection. So a connection is a distribution which varies smoothly from point to point on the total space such that it complements the vertical bundle at every point. So this means that whatever vertical bundle you choose, like Yaman says, so if this is the vertical subspace at, I don't know, P at X, should be on X, then for every point it can be this, this, but one of them. We get to choose, but we choose. So we just choose the complement of it at every point. Okay. Now let's continue. Okay, so now up to this brief review. So what have we done? So we had some problems with our lives. We wanted to transport vectors parallelly, but we did not know how to write this nicely because it depended on the path, and we had some problems how to write this formula. And so what we did was we first sat down and we decided what conditions we want on this parallel transportations. And then we said, okay, now to define this, guys, what can we do? So, and we said, like, if we know how to define these, so what will their properties be? And depending on these, we concluded that we need something called the connection, which is a choice we make for complementing the vertical bundle. And now we have the tool to define parallel transportation. We have to come back and say what a parallel transportation is in terms of this toolkits that we just constructed. Okay, so assume a connection is chosen. Then for each x in M and P in EX, linear map restricts to an isomorphism its inverse is called the horizontal lift. Actually, we're constructing the toolkit a little bit more. We know this guy from the preposition called okay. What did we say? We say that this is this restricts to an isomorphism. This. Now, you can ask why. Let's draw. This is E. This is M. This is X. This is EX. And this is P. I'm gonna make a sticker and I'm just gonna copy this everywhere whenever I talk about this. It will be much easier. But anyway, I've already drawn like 10 of them. So let's look at the tangent space. No, not this. Let's look at the tangent space at P. So it's hard to understand because I drove in 2 dimensions, but just please for me make a cylinder in your head, choose a point P on it, and stick a paper to it. Stick a paper at P. Okay. Then this is the tangent space. But what's this guy? This guy is the tangent space at P of to E of. Okay, I don't know how to read this actually. Should have been easy. Now we know that if we project this down, the kernel of this projection will be here, will be this, right? And what is this? This is VPE. This is defined as the points C in the tangent space, such that when we project it down, it gives us 0. So this means, so now back to linear algebra, back to 240. So we know that plus HPE is TPE, and we know that VPE is the kernel of this guy. So this means that actually if we have only this part, we can write an isomorphism from this to, sorry, not this. So and this was, okay, let me write it really nicely so it's obvious. To this. So if we restrict this on this guy, well, this should be isomorphic to this, right? This should be an isomorphism because the rest is just the kernel. So it's good. So it's perfect. So we now have to write the forgot the English word. Anyway, so we now have to delete the vertical parts of everything, and then the rest will be just the horizontal thing that we just chose with the connection. It comes with the connection. You buy a connection, the horizontal subspace comes with the connection, so you're happy, so you don't have to buy anything else. Okay. So another word that we're gonna define, a path through the total space E is called horizontal if it is everywhere tangent to HE. Then, given x0 in M and p0 in EX0, any path gamma t in M with initial point x0 lifts uniquely to a horizontal path in A with gamma tilde, so this is gamma tilde, with initial point P0, which is called the horizontal lift of gamma. And and its tangent vectors satisfy this is T, sorry. Now, here's the thing. By considering, okay, maybe before I write this, maybe let's go back to what we wrote. So what we basically say is we take the paths, we look at their horizontal lengths. Why do we do this? Because to eliminate the other things that were interrupting our paths, causing us to have different results for carrying the same vector over different paths. Yes, that's okay, that's a true sentence. So now what we do is we just look at the horizontal part, and that solves the thing. That solves the problem that we initially had. Because imagine the sphere example. If you had only been looking at the horizontal lift of the path, then you won't have a path like this, and you wouldn't have this problem. Because this whole problem appears because you're translating parallel relative to your manifold. And because your manifold has curvature, when even though if you transport it parallelly on a path, it rotates with the curvature. So that was the whole problem. But if you look at the horizontal lifts, even if you work on the total space, even if the total space has curvature, even if it's not a trivial, it has so much thing going on itself, we should be fine. Now that's a really good property. So now we say that by considering horizontal lifts for all possible phi in xi, x0, we obtain p gamma t from x0 to x gamma t, the parallel transport diffeomorphism. Ta-da! So that was the whole thing that we were trying to write. Now, this takes an input from this. So you tell it where to start, and then it takes your whatever vector that was tangent to gamma at start and makes it go there. So it makes it live in your total space nicely. And you don't even have to do it at 0 because now everything is well defined. So you can look at the tangent, whatever is tangent to gamma at time t. So that's really nice. Okay, now then for any x that's an element in the tangent space of x and m, we have this relation. So this is the covariant derivative that we wanted to define in the first place. This is given by whatever is tangent to this guy minus horizontal 6x. And now we have the last half of the paper. Okay, so we make a note here. So note. Not gamma. So all of these, whatever section you're on, you take the tangent, whatever it is, you project it and you will have the big X. And then we make an alternate definition of convection. That will be the last thing that I will discuss at least. So definition. a connection, on the fiber bundle P e to m is a smooth fiber-wise linear map K from T to VE such that Xi equals Xi for all what did I do? Yes, for all Xi in VE. So now this is an alternate way to define the connection. It's more algebraic if you prefer this. And if you ask us to how to relate the two definitions, quite simple. You just take the kernel of K and that gives you HE. So this is the same thing, right? For every point, you now take out the horizontal parts. So
Yes. So
something like this.
I just want to reiterate. We have this horizontal distribution, right? And it tells us, kind of which directions in the tangent space of the bundle are the same as the directions on the base space. Okay, and now that's what we used to call a connection. Now we're saying, how about we try and encode this in a slicker way? In a way that's a bit more convenient to work with, because before we were like, oh, I need to define like some kind of vector subspace at every point. That's maybe a little bit difficult. So instead, what we do is say, okay, I have my I have my horizontal distribution. So it's a horizontal vector space at every point. What I want to do is instead is encapsulate it in a linear map. So what I will do is I'll just have a linear map, which at every point of my vector bundle uh, tells me it takes in a vector in the tangent space and then tells me which component of it is vertical. And that automatically determines what the horizontal part is in the kernel. So this is just a more kind of slick way, in some sense, to define this whole horizontal um, distribution. I just define it as the kernel of some map, which is maybe a bit easier to write down in coordinates.
Yes, that's exactly the point. And this projection, the projection K from TE to VE is called a connection map because it defines the connection, right? Okay, so lastly, with this notation, with the connection map K that we have, we can now write the covariant derivative really nicely, and it will be just this. So this means, in words, the covariant derivative is literally the vertical part of the tangent map. Oh, I don't need, I've said this. Okay, anyway, no. Yeah. So we already said this. The covariant derivative is literally the vertical part of the tangent map. So, so for a section ST in E, and the path, I wrote something here which I don't understand. E. Okay, I don't think it affects the meaning. We have yes. But this was the thing that I wanted to say lastly. Do you have any questions? So that was the whole point. So we did understand what a trivial transportation was. We looked at the conditions. We looked at vertical and horizontal fiber spaces and subspaces for horizontal, and we defined the connections on fiber bundles. Okay. So any questions on this? Honestly speaking, I did find this very, very confusing when I first read about connections a year ago, I think. And then the second time I looked, it all made lots of sense, but lots and lots of sense. So feel free to be confused when you first heard, if you first heard of it.
Can I just see the last bit again? Sorry, I was like
Yes.
writing down stuff. Thank you.
I will share the notes.
Thank you.
Well, I will.
Yes, and I think I'll present next week, and so I'll do a little bit of review of this as well at the beginning, just conceptually. So yeah, it's good. I agree. This is the first time you read about it, it's confusing, and I don't think I found a good text that does it like quite exactly in actually this way. This was um, pretty like quite clear. It was good.
Thank you.
I thought it was good. Either you've done it very poorly or very well because either I somewhat understand things or I understand so little that I don't understand why I should be confused.
Yeah. That's okay. You'll be a little confused when we talk about gauge invariance because here, like we kind of define this general idea of parallel transport, but then in quantum mechanics, and I mean in general in physics, you often have this problem that certain you can have different kind of configurations in your vector bundle. So different vector fields are actually physically equivalent, and so you have to find a way to kind of make sure that you don't overcount things that are physically equivalent. Like maybe in physics 250 and E&M, you heard that the magnetic vector potential is defined up to derivatives of functions. So you could have two different vector potentials, like two completely different functions, which actually correspond to the same magnetic field. So they're physically equivalent, but it's two different functions. And so you want to avoid overcounting them. And for that case, you need to do something special. But I don't think we'll actually end up discussing this and kind of sweep these problems a little bit under the rug. But this story has a little bit more nuance in physics to it. But the idea that we've shown is exactly the same, modulo some additional details.
Okay. Good then.
Yeah, so I'll stop recording and